All right. Now we want to prove functorality globally. What does that mean? That means if we have a group, global group G, and we're looking at the automorphic forms for G, and we have another global group H, and we're looking at the automorphic forms on H, then we have, and if we have a homomorphism, C of HL into GL, the L groups, then attached to that, we have a way we are able to assign to a global stable class for H, a global stable class for G. So we're working in the context of the stable trace formula and stable classes. And just to make life easier, and I should say that this map will be local. In other words, we will work from the local pieces at a place V. So this will be the kind of transfer we want if each of these is at every place V. And that means it will be dual locally, and therefore by taking products in some global sense, it will be reduced to, if we have such a map of this to here, then we will like that so I don't have to say anything. It will be related to the existence of this map will be used. In every FG we have an FH, and FH is such that, so to speak, the inverse transfer is compatible with things. So that's what we want to prove. We want to prove if we have this and we have C, then stable classes of automorphic representation for H can be transferred to G in the sense that they can be transferred at every place, and so this at every place this transfers to this, and this transfer is dually related or inversely related to this kind of map. So that's what we want to prove. We want to prove that's possible at the global level, at the level of automorphic representations. So let me tell you what we do. We're going to use L functions. L of S pi is a stable class, but this L functions are the same within a stable class, and they're also attached to a representation rho of GL, a finite dimensional representation of that Galois group. So we want to use these L functions. I haven't defined, I'm taking for granted that every member of the audience knows how to define automorphic L functions. And although this makes it more difficult from the analytic point of view, I think ultimately one will have to work with the logarithm. That's a logarithm. This logarithm is a function of S. It's a function of S that converges for S sufficiently large. And we can write it for given pi as basically a summation of 1 over n to the s for various n's of stable trace of pi stable f, so n equal 1 to infinity. So we can find a function. This function will depend upon rho. And it will doesn't depend upon s. We can write it as such a thing, but it will depend upon n. So what we can find, such an L function can be defined as the trace of pi of st of f of n rho. So now we expect that this function can be analytically continued up to s equal 1. Remember that we're assuming that we're just setting aside, and in order to avoid explanation, those representations which are not of Arthur type. And that means that we expect that these representations will be holomorphic for s greater than 1, for the real part of s greater than 1. And then they may have some poles on the line real s equal 1, but they'll be all lines with first order poles. And of course, there's no zero, if this function, L function, there's no pole 0 on that line, then there will be, the logarithm will have no poles. So the derivative of the logarithm, I think, do we want to do? I guess we want to do something like that. I hope that's right. So now, once we have this, we can say, well, I'm not going to consider one of them. I don't know anything about a single automorphic representation pi. I will sum this over all, say, cuspidal automorphic representations. So now if we're not careful, we'll get into technical questions about the trace formula. But basically, we're going to sum it over all representations, and we're going to multiply by the multiplicity of pi stable. Now, the multiplicity in this stable theory may not be integral. It may be a rational number. So now, we haven't asked anything about functoriality yet. We've just said we're going to consider this. And we're going to consider this for various rho. Then we ask ourselves, well, what are the propositions upon which the theory is based? They're based on the following fact, that every stable class is really associated to a subgroup of GL. That's what functoriality says. For example, one knows for GL2, there are some representations which are in some sense, I would say, hadronic or thick, namely, same thing. Then they're somehow associated to a representation, to a subgroup, which is the full GL2 or SL2. And those are the functions those are the representations which behave reasonably from the point of view, I forget the name, it's Tate and somebody else. I'm sorry, I've forgotten that. Second person. But the L functions behave very much as though they have a specific asymptotic behavior, which is that, I'm sorry, I can't fill this in. I'm old and my memory for names go. So we know that from the point of view of this Mr. X Tate's the Japanese name, theorem, Sato Tate theorem, that there's some representations whose L functions behave as though they were the image here, the subgroup associated with pi of st was the full group. So they are functions which cannot be transferred by functoriality from lower dimensional groups. This, and then this, at least if rho is an irreducible representation, has no pole in real s equal 1. On the other hand, if pi of st is associated to some group, as in the Sato Tate, then what happens is that this L function will, and if rho, if the representation rho restricted to that subgroup contains the trivial representation, then in L, or in this logarithm, will be an additive term that looks like the zeta function. Looks like the zeta function, and that will have a pole. So that will have a pole. So what is that the poles of this function, like on the line real s equal 1, or on the line on the point s equal 1, are determined by the subgroup to which this is associated. So we think, knowing functoriality, we think it has to, that implies it associated to some subgroup. So now think about it. So we have this situation. We've summed over all pi. And some pi are hadronic in the sense they're associated to full G, and then this function, provided that rho isn't the trivial representation, say it's irreducible, it's not the trivial representation, then this function has no, for the given pi, this has no pole at s equal 1, or on the line of real s equal 1. But if it comes from a smaller group, then we can choose a certain rho such that its restriction to that smaller subgroup contains the trivial representation, and then there will be a pole up here. So, in other words, there's the contribution of a given pi of st reflects or tells us indeed the subgroup to which pi of st is associated. So here's the thing, here's what one wants to do. One wants to use the trace formula to pick out a particular group, or something like that. One wants to use this. The trace formula is going to tell us which pi are associated to which group, because the trace formula is going to tell us where the poles of that lie and what the nature is. For which rho it has, so it will tell us which rho, and there's a contribution of pi to the pole at s equal 1. Now, what does that mean? Let's try to imagine what it means. So how are we going to make this work to our favor? When we say, we'll take the trace formula. We'll take the trace formula for all of G. And for rho, any representation, any irreducible representation. Then immediately we see that, according to what I say, that there's no pole on the line real s equal 1 contributed by those things which are hadronic. So the only things which are contributing are those things which come from functoriality by some subgroup of GL. Doesn't necessarily have to be a connected subgroup. So we say, well, look at this. See, this, whatever this is something, when we sum over pi, for which we have a formula, namely the trace formula. So we look at the first part. We look at the whole thing, and we say, well, from the whole thing, we know there's no contribution except for those things for which implicitly pi comes from a subgroup. So let's take the whole thing and let's subtract from it. So let's take the whole thing, and we know that those things, in principle at least, which are hadronic, whose image corresponds to the whole group, won't contribute anything to the asymptotic behavior of that as s approaches 1. But now then, let's go to the next stage. Let's say, well, okay, but we know that anything that's left belongs to some subgroup. So why don't we just subtract everything that comes from some subgroup? So we start this, and then we know that those things that are hadronic don't contribute. Let's start and subtract from the whole trace formula those things which correspond to some proper subgroup. We'll do that. Results should be, now we know, so this is something in which we have the trace formula. The trace formula should give us a concrete expression. So we have a concrete expression for this. We have a concrete expression for this too, because we have a concrete expression for each subgroup. So we have something for that, and their difference should be 0. And if their difference is 0, If we look at the difference of the trace formulas and we see that the difference is 0, then we'll have concluded that indeed all the representations of G that are supposed to come from subgroups do come from subgroups, because they're there in the trace formula. I mean, we can do something a little bit different. In other words, in this L function, we can take this and convolute it by a product over a finite number of V, F, B, where these are arbitrary. And the trace formula looks as though you can't separate in individual pi, but you can separate individual pi because you could introduce an extra factor like that at a finite number of places. So we could do that. So we do it, and then we should get 0. So all we have to do is apply the trace formula here and apply the trace formula here, look at them together, look at the analytic, at the asymptotic behavior, and show it's 0. Well, that's an exaggeration, of course, because some representation pi could be the functorial transfer from two different subgroups. We could say, well, it comes from the subgroup G1, but it may come from G1 through through a subgroup. It may come through G1 from G1 by means of a subgroup of G1. So we will have subtracted it once for G1 and once for G2. So we cannot, there's some telescoping. There's some telescoping, has to be taken into account. So that's all you have to do. Now it's perfectly reasonable, except for what? One thing demands a mastery of the trace formula. All right. Secondly, it demands a mastery of the analysis of Dirichlet series. Dirichlet series. So, really hard analysis with Dirichlet series. And then it demands that we take into account the telescoping. But in the end, it may turn out we can do all these things. We can do all these things and we get a formula. Some concrete formula. We're going to have to show it's 0. So that will be, at the end of it all, you may have some hard problems, the Diophantine analysis to solve. Now let me just make a comment on that. That's basically the strategy. And it's the only reasonable strategy we have. But what we need to do is have an adequate command of the mathematics in order to go through all these steps. And then what will happen at the final step? See, the final step will be some concrete formula, and this will be the final contribution will have a Diophantine expression. And we'll have to show it's equal to 0. Now, there are various cases where such as those quaternionic groups and so on, where this might be possible, but just recall what we would get if we worked with GL1. GL1 And if rho here, so this, the L group is GL1, and we could take representation x into x to the L. We could take L to be a prime, for example. So we could try that. So we would be doing the trace formula for GL1. And so we would have this. We would have, for GL1, the initial sum. I mean, we know what the trace formula for GL1 itself is, the sum over characters. But then there are these subgroups. The subgroups, of course, of GL1 are all 1, which is not, but the L group has in it a Galois group factor, Galois of k over f times GL1. So a subgroup wouldn't really just be 1, it would be the Galois group of k over f. So what we would have, in addition, we got to the end, we would have contributions of representation, one-dimensional representation of the Galois group, and into GL1, and then we'd be composing that with the nth power. So what the second contribution, the one which we subtracted, would be determined by the extensions k over of f that have a Galois group, which is the cyclic group of order L. So what we have to show is that the contribution from the cyclic group of order L is equal to the contribution to this of a certain class of representations, those associated, as I said, to a character of order L of the adelic group GL1. And of course, that is exactly what one does in class field theory. So that's the concrete calculation that comes at the end, say in Hasse, in the proof of the existence of class fields and the structure of class field theory. And you see it comes out very simply from this point of view, except that this, we're asking that it be done in general, and the whole structure of the proof depends upon the existence of functorality, and we just exploit it if we can. And I think I said in the first hour that this is no easy matter. One has to know a lot. One needs a lot of patience, because you're going to have, it's not easy. I mean, as soon as these representations, as soon as these finite groups, that subgroups of G and so on, start to appear, one is the calculation of the number of Galois groups with the number of fields with that group as Galois group and so on, becomes much more complicated. And the number and the results of the trace formula will again presumably become much more complicated. But that is, in my view, what I think has to be done, and it has to be done with someone with a great deal of competence and a great deal of courage. All right. So that's all I want to say about functoriality and its proof. So now we can go on to the second topic, which is the geometric theory. So let me erase everything here. And let me go on to the second point, which is the geometric theory. Now, let me first make an observation, and I have it here someplace. Let's think about Fourier analysis. Because what I'm looking for is a theory which is a spectral theory. The theory of eigenvalues. So you see, let's look at Fourier analysis on Rn. So that's the simultaneous spectral theory of operators 1 over d dx1, 1 over I d dxn. And the standard Fourier theory is the theory of the fact that f goes to f hat of y equals integral over Rn f of x e to the I x dot y dx. So that this is an L2 isomorphism. Now, in my view, this is the principal form, primary form for harmonic analysis on Rn. And then there are various other forms which you may or may not have studied when you were young. Laplace transform, Paley-Wiener theorem, space of Schwartz functions, and so on. Space of tempered Schwartz functions. Now, and there are various modifications of that. These are all interesting theories, but I think they have all to be considered as derivative theories. Some of you may, some of the audience is not this gentleman in front of me, Tony is still there, but some of you may think that this is not so. I think it's so, but there's been, I think, a distortion of the geometric theory because most of the practitioners of the geometric theory are really algebraic geometers. And algebraic geometers, they want to think in terms of sheaves, and stacks. And I feel that for the theory, this is inappropriate. That one has first to do an L2 theory. So the question is, how do you do an L2 theory? And this, my feeling also is that these things quickly become very soft. But that's maybe a personal opinion. I don't want to force down anyone's throat. So these were sort of general remarks with which to start. One has to learn what these stacks are maybe not important, but there is something that's important that's implicit in the notion of stacks. So let me just indicate, and I think I can do this more briefly than I could treat the first case. So we're going to do the geometric theory. Now, it's going to be, let's see, where am I here? Yes. So if we're going to do it, we're going to do something which, as I like to think, so we sort of can say, look, Ma, no sheaves, no stacks, something like that. So now, but what do we need to do then? You see, the geometric theory is ordinarily treated, and I think we should begin with that theory, as an unramified theory. That means we take G of A, and this is an adelic sense in the sense of the function field of a Riemann surface, and we divide by the product over V in the Riemann surface G of OX, where these are the group with elements from the ring of formal power series at the point X, so of V, so let's put X, and then divide on the other hand by G of F. This is, one knows, one can find it in various places. The appropriate moduli space for the G bundles. Now, this space is in a certain sense, it's a moduli space, one proves that, but it's a difficult space because this group one is not dividing by a discrete group, one is dividing by a continuous group. And it has taken me a while to learn how people think about these things. So this is a continuous group. We divide out by that. So how do you divide this group, so you have to be a little bit careful as to just what this is, but that aside, it turns out that basically this quotient is equidimensional. I find some aspects of the argument a little bit slippery, and I don't really appreciate them yet because the proof which uses Riemann-Roch, or a form of Riemann-Roch which is given in, I find in Wikipedia as Weis Riemann-Roch. The Riemann-Roch theorem that enables one to show that although the dimension of the stabilizer of a fixed point is moving around and so on, this quotient is in fact a variety, so perhaps singular variety, but everywhere the dimension is the same. So now I pretty much understand the argument, but there are some questions I have in my own mind, but there I think about the argument. I don't, where there are singularities and so on. I have a little bit of trouble with that. Now, so I want to consider the whole thing. I remind you that, and this I find a little bit unfortunate, that for reasons of their own, the algebraic geometers consider only part of this space. They only consider the space which is formed by so-called stable bundles or semi-stable bundles. But I want a theory which looks just like the theory, a spectral theory, and which looks like this theory of L2 GF GA over an L2 theory with Hecke operators. Now, the Hecke operators in the theory that the algebraic geometers have constructed are operators, are correspondences and define operators on sheaves. So we need to pass, so to speak, from some kind of, we need to pass somehow to regular operators on Hilbert, to genuine operators on Hilbert space. And the thing is that the techniques are still there. For example, you want this space to be a metric space. Now, I found it, and I can't do this myself, but there's a paper of Atiyah Bhatt, and they basically tell you how to do that in the context of Hamiltonian mechanics. So they basically, but I don't know whether Bhatt was intimidated by Atiyah as an algebraic geometer or what, but they confined themselves to semi-stable bundles. So I have to understand how to make their definition in general. That will give me a metric space. It will give me something space with a Kählerian metric. I hope so, but there's something there that one doesn't, I don't know. And then once you have that, you have to convert the Hecke operators into integral operators. Now, you convert Hecke operators as defined geometrically into integral operators by some form of the Gauss-Bonnet theorem. Let me put it this way. Gauss-Bonnet theorem. Since we're, to some extent, in Oxford today, that may be the index theorem. But in other words, the material for introducing the Hecke operator, for creating a metric space by Kählerian metric, and introducing the Hecke operators as integral operators really seems to be there. I just don't master the necessary material well enough to say definitely that this is so. So that's really my task. Now, we're dealing here with a task that I think, is within the range of someone of my age and my talents. Namely, the material is really there. There's nothing so very hard if one wants to take this geometric theory and reinterpret it as a spectral theory on a Hilbert space. The Kähler metric is there, measure is there, the Hecke operators become integral operators. One just has to be sure that they become commutative family of integral operators and so on. But what does one, so, and then that's not all we want. It's not all we want, but that's something we want. Now, I want to say something as an aside. I want to say something. As an aside, it's the following. What kind of, do we expect a theory like the classical theory, like the theory for automorphic, number theoretical automorphic forms? Well, I remind you that number theoretical one is a theory of Eisenstein series. It's a spectral theory. And there's spectrum which is continuous, which is a discrete spectrum. Say the cuspidal spectrum. And then there's the spectrum of dimension 1, 2, up to the rank of G. So if G n is up to dimension n. And that's how it works. So one sort of sees that, and this is a one-dimensional continuous spectrum, a two-dimensional continuous spectrum with perhaps some discrete. So one expects something similar for an arbitrary group G. So one expects some kind of, so this corresponds to the fact that there's some, that in the classical case, there's some kind of cone of dimension n, and we're doing the differential geometry in that. We're doing the spectral theory, infinite dimensional spectral theory, on some such domain. If it were a line, we'd just have a continuous spectrum and a discrete spectrum, which corresponds to the ordinary theory of, say, of second-order differential equations. Now, here's what I want to say. If you think about this, from the point, how should, I just want to observe this because it's rather fascinating. What I discovered is that the geometric theory is richer than one is allowed to guess from some of the standard expositions. It's geometrically much richer. Namely, suppose, what does it mean? We have to think. We want, in the geometric theory, it should be the same thing. There should be a discrete spectrum plus spectrum from 1 up to n to the rank of G. So let's take the rank of G n equal 1. That's easier to envisage. The geometry is easier to envisage. For example, here it's basically a line. It's a line. In the ordinary classical theory, it's maybe a half line with a circle in it, but the circle doesn't matter. Now, if you think about G, so one has various fields. One has f of genus 0. And in that case, what one knows is that this space, the moduli space, so the GF, GA over product of GOV is discrete, and it's just Z plus. That's a theorem of Grothendieck. And so, indeed, that's the case. There's no discrete spectrum, and there's continuous spectrum of rank 1. If you do genus 1, well, there is a paper of Attia who discusses this quite at length. It's a very useful paper. In other words, if you come to the subject as a complete novice, then it really helps to read what Attia has written, because you avoid guessing things that are unfortunately obviously false. It's easy to run. So here, in the genus 1 case, it's a similar situation, namely, it's like the genus 0 case, namely, there are discrete pieces, and these pieces are two-dimensional. So, I want to talk GL2. I'm dealing with GL2. Whatever I said about GL1 was false. I'm dealing with GL2. So for genus 1, there's some two-dimensional piece in the center which is unknown, and that's going to contribute to the discrete spectrum, because the discrete spectrum of an operator on a compact space. I mean, the spectrum in a compact space tends to be discrete. And then there are basically, so it's GL2, so it's rank 2. So we really have Z plus, Z plus. They're twice. And these things here basically correspond to the direct sum of the line bundle of degree 1 plus another L plus L prime. So this is of 1 degree K1, and this is another degree 2 K2. So it's pretty much so, it's not quite that, but it's pretty much so that there's a two-dimensional piece, which is more or less compact, and then there are these pieces, one for each integer. Maybe K1 minus K2 has to be bigger than 2 or something, but there are these pieces, and so this L is a line bundle, so the line bundles for genus 1 form a one-dimensional complex space, a two-dimensional real space, compact, and then there are line bundles for K2. It's the same structure. So what we see here is that there's this piece, which is basically the curve times itself times Z plus, Z plus, Z plus. And this Z plus and Z plus corresponds to the two ranks. Now, what it seems to me, and this is something that one has to do with genus greater than 1, and I haven't seen this discussed, although I'm sure people who have thought about it know it. The moduli space has a very curious structure, namely, it has pieces like that, where now, of course, these pieces are of dimension G, where G is the genus of the curve, and so we're still dealing with GL2. It's also the genus of the curve, so there's those pieces in there, and then we have a Z plus plus Z plus. Again, but that's not all we have. What happens, I really can't understand this yet, is that we have a piece like that. So we have pieces like that, just as we had them for for the elliptic curve, they were discrete, but for curves of higher genus, they're not discrete. They're somehow sitting in there. Then another one sitting in there when we change K1 and 2, so on, and they're joined. They're joined somehow. And these pieces that are joined are, as K1 and K2 get bigger and bigger, somehow shrinking down, so they don't have an effect on the spectrum. Now that's the picture that one gleans from just looking at the literature, but I don't know for sure that it's true. but it's pretty much what has to be true if the suspicion that I expressed at the beginning is true, namely the spectrum in the geometric case looks pretty much like the spectrum in the arithmetic case. So that's these things. I think it would be nice if one had a really clean, discrete, proper theory like that, and that is somehow, it looks to me as it's doable. You just sit down, you learn what's available in the literature, and you think it through, you get it. It's not at the same level as what we had before for problem one, for functoriality. There's just, I want to make one further comment. It's the parametrization of the spectrum. So we have G and we have GL. So we have bun G. That's this double two-sided coset space whose structure we've been considering, and we have the same thing here. Now, what it seems to me is that there will be this question of Ramanujan's conjecture, namely, are the spectrum of the Hecke operators, there's a different spectrum for the Hecke operators at each point, and this spectrum at each given point is an element of, is really it's a semi-simple element of GL. Then as we move around the point, move the point around, this element moves around, and it moves around, what do I want to say? It has to move around. So really, as it's moving around, it gives you a conjugacy class in G of F, where this is the function field of the Riemann surface. So it gives you a conjugacy class, maybe even a semi-simple one you'll have to prove. So that the spectrum is parameterized by these objects, semi-simple conjugacy classes in G of F. So these are unitary connections. Now what, if you look at Frankel's expositions and papers, as I've done with some assiduity, you see that the same thing is expressed, but expressed in the language of holomorphic connections, flat connections, and so on. So this, now, so you have to, now, one can pass, and if I look at the literature, without having mastered it, you have harmonic functions, you have holomorphic functions, and you have unitary connections, and you have holomorphic connections. Now, so everything that I find, say in Frankel's expositions, is expressed in terms of holomorphic connections, of flat holomorphic connections. So there's this transition from flat holomorphic connections to unitary connections. But flat holomorphic connections will give you more. In other words, they'll give you Laplace transform, Paley-Wiener theorem, Schwartz, and so on and so forth. So the algebraic geometric expression, which allows you to talk flat holomorphic connections rather than in terms of unitary conjugacy classes, is broader, but it doesn't allow for such precise and such rich results. So that's all I wanted to say here, that in this part, in connection with the geometric theory, that one should be able to, if one is an assiduous worker, create a theory, an L2 theory, which doesn't contain everything that the holomorphic theory contains, but is a basis for a really solid understanding of the moduli space and the functions on it and the Hecke operators on it and so on. If one concentrates, as in the classical case, on the L2 spectrum. All right, that's it for part 2 is finished, and we can take a 15-minute break and go on to what I think is the rest.